Welcome back, everybody. This is episode 3 of this little series in which I'm trying to give you a demonstration of the capabilities of Cerberus 2080. This is release 1.2, probably the last release of Cerberus, since the delta with comparison to the first release was already so small anyway. We've covered in episode 1 the basics of the functionality of Cerberus, what it could do. In episode 2, we looked at the flexibility. We talked about there being no ROMs in this computer. The ROMs are virtual. The BIOS is stored in the built-in flash memory of the I/O controller. So you can put an operating system anywhere. You can put a basic interpreter anywhere. And in episode 2, we looked at the Ruby OS operating system by Gordon Henderson, which was mapped to the low memory and executed by the 6502. And also a port, also by Gordon, of BBC Basic Interpreter version 4, the best BBC the best basic interpreter of the 80s, which was mapped to a part of the high memory and also executed on the 6502. So we've seen some graphics, block graphics applications running on BASIC on top of Ruby OS on the 6502. So that was an illustration of how you could make Cerberus the machine you want of it, because there are no ROMs here. The memory map is largely programmable by what you put in the BIOS, and the BIOS is an Arduino sketch written in C. So you can basically make of this platform almost anything you want, so long as you stick to black and white graphics and 8-bit computing. Today, we are going to do something else. Today we are going to look at the high-resolution graphics capabilities of Cerberus. Cerberus is a character-based architecture. Here you have the video memory, and here you have the character memory. And this stores 256 different character definitions, each one of them consisting of an 8x8 matrix of pixels, so 64 pixels. Now, because the character definitions are stored in a dual-ported SRAM, which can be written into just as easily as the system memories can be written into or the video memory can be written into, all character definitions are redefinable very quickly on the fly, simply by code. So you could regard these 256 characters, if you're doing a graphics application, as 256 sprites. And I'm using the word sprite here in an admittedly loose manner. Cerberus does not have the notion of a transparent pixel. So strictly speaking, these are not sprites, but it's a black and white architecture. So in practice, you almost always can use them as sprites, so long as you create little overlapping sprites for areas in which two things overlap with one another. You have to do that explicitly. But then again, you have 256 sprites. If you put 256 characters simultaneously on the screen by loading their IDs here in the video memory, you would also have a kind of virtual bitmap mode by just redefining each of those 256 characters to be a piece in a larger pixel map puzzle, so to say. So let's look today at what Andy Toone did with Cerberus. He did a port of Manic Miner, a very famous game from back in the 80s. Was made famous by the Spectrum, the ZX Spectrum. And Andy not only ported it to Cerberus, he started a fairly educational project about how to write an assembly program from scratch on the 6502. So he basically rewrote Manic Miner from scratch, made his own version of it, leveraging in full the potential of Cerberus to use character bitmaps as pseudo-sprites, so to say. So that's what I want to show you today. Now, as we've seen in episode 2, Andy, of course, didn't resist the temptation of writing his own version of the BIOS, and he had good reason for that. Manic Miner doesn't need to load or save things, so the reason for his writing another BIOS was not the same reason that Gordon had. But he wanted a 50 hertz interruption being provided by the I/O controller to the 6502 because it made his game development easier. There are a couple of other things he did. One of them was that because he was developing or writing the code on an assembler on his PC, he didn't want each time to take out the micro SD card, put it on his PC, load with the new version of the code, and put it back. So what he did, he modified the BIOS such that he could download new versions of the game straight from his PC via FTDI. So he would just connect the FTDI adapter here and then compile his assembly code and download the resulting binary through FTDI straight into the micro SD card without having to remove the micro SD card. And that's a pretty nice feature. I almost was a little bit like, oh, darn, I should have thought of it myself. But the credit is fully his. He called his BIOS, I think, the XFE BIOS. He changed the memory map a little bit, the location of the mailbox and the mail flag. He made a few changes. So the first thing we will do now is to load his BIOS, the XFE BIOS. So let's connect the FTDI adapter. And then with one simple command from my PC, we will load the new BIOS. So let's go and do it. And there we have it. The new BIOS is being uploaded. You see that in the little blinking LEDs in here. It will have to upload it and then verify it, and then we can just load Andy's game, Manic Miner. And then the BIOS, of course, resets itself automatically. You can see there on the right lower corner the XFE version 1.0. That's Andy's BIOS. So we are loaded now. I'll go to fast mode, 8 megahertz. Although I think in this case, it doesn't matter much because I think Andy has taken care to make sure that the timings in the game are all correct as they were in the original version. So whatever speed you run, I think the game will probably take care that things don't happen too fast. Because one of the motivations for having this slow mode in Cerberus is that if you do a vanilla port of some of the old games to Cerberus, they may work so fast that they become unplayable. So that's why I put this slow mode. But I noticed playing Manic Miner that it didn't matter. The game was playable anyway. So let's load Andy's game. The name is... oh yeah. Manic.bin. Manic.bin. Let's load it up. It takes a couple of seconds to load it from the micro SD card. So if we go to the code area now, those are the opcodes of the game. Now we just run it. And the first thing the game will do, of course, is to update the definitions of the standard character set here in the character memory and turn a number of those characters into basically graphics blocks, not block graphics, but graphics building blocks, pseudo-sprites, so to say, virtual sprites that do not have transparency, but can otherwise be treated as sprites. And he does that even for the title screen. As you see there, those large letters, the large font, Manic Miner. Cerberus has no native concept of fonts like that. So what Andy is doing is he's basically using the character set as a sprite set to build this title screen, which is pretty cool. It's pretty cool. So let's, I'll try to play it. I used to be good at it when I was a kid. Actually, it's kind of mind-boggling for me as an adult to play Manic Miner, one of my favorite games from the early 80s, on a computer I built. And that was my dream back in the early 80s, to build my own 8-bit computer. So it's like, wow, it's a temporal vortex in my mind, a big arch of my life. It's coming to closure now anyway. So let's go in and see what we can do. Now you will notice there is no sound, but that's not an intrinsic limitation of Cerberus. We've seen in the previous episodes that Gordon implemented a BIOS that has full two-way communication between CAT and the CPU, between the I/O processor and the CPU. So the same thing can be done also for games, in which the CPU sends a request to the I/O processor to produce a sound, to produce a certain tone. That's totally doable. It's just not being done in this case. So the game is right now silent. Actually, Andy told me that he even removed the key strike sound of my original BIOS because it bothered him. So I think he prefers things this way, but it is certainly possible to give beeper sound or buzzer sound to games. So I think I've completed the first cave. Yes, I did, although I was talking. I managed to complete the first cave. The second one is a little bit trickier. Oh, no. Oh, no, I forgot. I forgot that. Okay, now I did it right. The animations can be done, of course, in two ways. You can, on the one hand, just change the pseudo-sprite that is on a certain part of the screen at one time. What? Did I die? Why did I die? What did I do? I didn't see what I did. That was so wrong. Or you can just change the definition of one character such that by changing its definition and with the same character on the screen, you create the illusion of animation. As a matter of fact, this is what I think Andy did for at least the conveyor belts. If you look at the conveyor belt on the mid to bottom left, I think the easiest way to do that is to just put the same character on all the positions of the conveyor belt on the screen, keep the same character there, and update the definition of the character to create that illusion of movement. That's at least how I... okay, that maybe I missed a key somewhere. I don't know. But let me try to show you to you again to explain. You see the conveyor belt in the middle of the screen where that bad guy is running around, pacing around. I think the easiest way to do that, and because it's a long conveyor belt, so it would require over a dozen instances of a character, maybe 24, to put on the screen. I think the easier way to create that smooth animation, that movement of the conveyor belt, is to use only one character for the entire conveyor belt and then update the definition of that character to create the illusion of movement. Because if you look at the movement, only two lines are actually changing, the top line and the third from the top of the 8 lines of a character. So it's only 2 writes to the character memory to do that animation. And if you would try to do the animation by using a different character for each frame of the animation in the entire conveyor belt, you would have to do a couple of dozen writes to video memory. So it's easier to just sort of change the pseudo-sprite as opposed to using another pseudo-sprite for every frame of the animation. I don't know that this is how Andy did this. I think I would do it that way, but I trust Andy more than I in these matters. He's much better at leveraging the capabilities of Cerberus than I am. I'm not really a programmer, I did programming in my life because in this day and age, computer engineers, half of what they do is programming, and some of them, everything they do is programming, but it's not really my thing. Anyway, this is it for this episode. This is what I wanted to share with you. Oh, I hit my head on the stalactite. This is what I wanted to share with you in this episode. This pseudo-sprite capability of Cerberus. Just to give you a context, the way Cerberus starts up, it has no character ROM. So for it to even give you a startup screen, what it does is, as soon as you turn the computer off, the I/O controller running the BIOS will go to the microSD card and load a character definitions file. And it will load it up and then pass it on via spacer to the character memory and load all 256 character definitions here in the character memory. And only then it will give you a startup screen, because to give you a startup screen, it needs to know the character definitions. Otherwise, there would be just garbage. So that's what happens in a fraction of a second when you turn Cerberus on. All of this happens very quickly, loading the character definitions from here into the I/O controller via spacer into the character memory. And of course, we cannot leave those character definitions as they are right now, the ones for the game. We cannot leave those pseudo-sprites intact if we go back to the BIOS, because otherwise there would be no text anymore. And some of the letters would be graphics characters. So if I press ESC during the game, the first thing that will happen, and that's programmed into the BIOS, is that before the BIOS gives you the BIOS screen again, it will again go and load the character definitions from the microSD card and via spacer to the character memory, and all that will happen in a fraction of a second, and you get the BIOS screen. So look at this. I'll press ESC now, and you try to see what will happen. You see, for a moment there, before the screen was cleared, you saw what the original definitions of those pseudo-sprites were. I'll do it again. I'll run it again so you get a feeling. So what you're seeing on the screen now is a bunch of the normal characters of Cerberus just redefined. If I press ESC, the original definitions will be reloaded before the screen is cleared. So you see how Andy started. You see? Did you see? You saw the text characters that he was using to create that large font that you saw. So that's how Cerberus works. It's a mixture of text and graphics. It's only one paradigm of graphics building blocks of 8x8 pixels. I will press escape again. You see, those are the actual characters that were there. I personally think this is a nice educative paradigm, because it does away with the notion of modes. There is only one mode in Cerberus, and it is text, and it is graphics. And that's what is made possible by just doing a black and white architecture and using dual-ported memories. You can very quickly change the pseudo-sprite definitions just as quickly or quicker than changing the characters used on the video buffer, in the video memory in here. So I hope this has been fruitful and interesting to you. In episode 4, the next episode, which is probably going to be the last episode, at least for a while, we are going to look into the performance of Cerberus. So in episode 1, we looked at the basics. In episode 2, we looked at the flexibility of putting virtual ROMs, kernel ROMs, and basic ROMs in different places. In episode 3, we looked at the graphics. And in episode 4, we will look at the performance. And we will do that using Dean Bellfield's port of BBC Basic for Cerberus's Z80. In episode 2, we looked at BBC Basic Interpreter version 4 on the 6502, ported by Gordon Henderson. And in the next episode, we will look at Dean Bellfield's port of BBC Basic for the Z80. And then we will run some basic benchmark tests on that and compare that to other computers out there from the 80s and even a modern computer like the ZX Spectrum Next. And we will see how Cerberus stands up to all that. Of course, Cerberus was not made for performance. Cerberus was made to be an educational platform. It uses only 5 volts through-hole technology. So it's never an apples-to-apples comparison for these benchmarks. But for the sake of curiosity, we will run some of the benchmarks that Dean has, and we'll see where we stand in comparison to a few other computers. So that's what's coming next time. Until then, stay safe, stay healthy, and I will see you then. Take care.